Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is a second video on Newton's method, one of my favorite topics in calculus. It is really very cool and should technically be introduced much earlier than it is in most calculus books. The reason why is you can use it all the time. In fact, this should have been introduced once you were done taking derivatives. To be honest with you, I just didn't do it I never do it that way in my courses, but I'm thinking about changing that up. It would be really nice because then when you run into these problems, you can actually find the roots. So let's go ahead and do that. It is assumed, by the way, that you've already watched my video on Newton's method itself. I'll just write down the method as far as the iterative scheme. You take a guess, call it x sub 1. Then from that point forward, x sub n plus 1 is just going to be x sub n minus f at x sub n all over the derivative of f evaluated at x sub n. So that's the heads up. Also, you do not want the derivative at x sub n to be even near to 0. So you don't want it to be near to 0 at all. Obviously, it can't equal 0 because you'd be dividing by 0, but you don't want it near to 0 either. And you want your initial guess as to the root of this function to be somewhat close to the actual root, but it doesn't have to be exactly the root. All right, so let's rewind the tape in our calculus history. Prove that this function has exactly one real root and that the root is between -1 and 0. We'll start there. So we want to prove that it has exactly one root. Well, if you note, f is continuous. Definitely is. It's continuous. C-O-N apostrophe T is my notation for continuous. So f is continuous basically on all real numbers. So on the real number system or on the real number line, that's fine too. And let's see, and f at 0 is 5. Sure is. And f at -1 is, let's see, -1 minus 4, that's -5, minus 3, that's -8, plus 5, that's -3. So it's -3. So the function goes from a positive value to a negative value. In fact, I should say it the other way around, right? Because x equals -1 occurs before x equals 0. So the function goes from a negative value to a positive value on the interval from -1 to 0. So it goes from some negative value to some positive value, and f is continuous, which means f must cross the x-axis at some point between -1 and 0 by the intermediate value theorem. So thus this implies f of c is equal to 0 for some c in the interval from -1 to 0, and this is by the intermediate value theorem. So that's the first part. That's called the existence part. We've shown that there exists a root between -1 and 0. If you need a review on the intermediate value theorem, I do have videos in this video series on the intermediate value theorem. Highly recommend you watch them if you need a review on that. The second part we need to do is prove that the root that we have here, which we don't know its value, but the root that we have there is unique. In other words, we want to prove that there are no other roots to this function ever. So this is the uniqueness part. And again, if you have not seen my videos on existence and uniqueness proofs, it's in the Rolle's theorem area of my YouTube channel. So I highly recommend you review that. The fact is, we have a function, it's continuous on the interval. It's actually continuous for all real numbers, but it's specifically continuous on the closed interval from -1 to 0. And the derivative of the function, f, and I have to compute that anyway, so I might as well just do it right here. The derivative of the function is 7x to the 6th plus 20x to the 4th plus 3. That's a polynomial, and polynomials exist for all real numbers, so therefore this derivative exists on -1 to 0, the open interval. Those two statements right there, 1 and 2, mean that I could use, or imply that I can use the mean value theorem. I don't want to here, but I'm just telling you, we could use the mean value theorem here if we wanted to. But again, if you've seen my video series, then you kind of know where I'm heading here. Let's, instead of saying, well, let's find that exactly one root, let's find it. Instead of doing that, let's suppose that there is actually, or there are actually more than one root. So let's say there's 2 or 3 or 4 or 20. But once you say there's more than one root, then you have 2 at least. So let's assume there are 2 roots. Of course, saying you have more than one root is the same thing, right? So you have more than one root means you have at least 2. So given that, we know there must exist 2 numbers such that f is going to be 0 at those 2 numbers, because we're assuming f has more than one root. So f must turn into 0 at 2 different values, where, maybe I should put a comma there, where C1 is not equal to C2. And because we were technically working on this closed interval, we're just going to say that C1 and C2 are in the interval from -1 to 0. Although they don't have to be, because the reality is our function is continuous on all real numbers and differentiable in all real numbers. So you could technically use this argument for all real numbers as well. But let's just go ahead and just say C1 and C2 are in the interval -1 to 0, sorry, -1 to 0. Okay, so assume f has more than one root, thus there exists a C1 and C2 such that f of C1 is equal to 0 and f of C2 is equal to 0, where C1 and C2 are not the same, and C1 and C2 are in that interval from -1 to 0. Great. Since f is continuous, check, and f is differentiable, check, and f at C1 is equal to f at C2, check, we can use Rolle's theorem. And Rolle's theorem says the following: by Rolle's theorem, there must be a number between C1 and C2, and I'm assuming C1's less than C2. Yeah, that's fine. Okay, such that f prime at C3, f prime at that number, is 0. In other words, because we know it's continuous and differentiable, and because we're assuming that our function became 0 at C1 and C2, it must go up and come down, or go down and come back up, or it could be flat the entire time, but there has to be some number where the derivative is 0. Okay, again, logical deductive, or deductive logic, we're totally fine here. However, there's an issue. F prime of x is equal to, where do we compute it? 7x to the 6th, what is it, plus 20x to the 4th, plus 3. And the first 2 terms are never negative. The last term is always 3, so this is always greater than or equal to 3, which it contradicts the fact that we have a number where the derivative becomes 0. So this is a contradiction. I'm going to write that in red, a contradiction. And so because we have a contradiction, we must have made a bad assumption somewhere. And our bad assumption was right at the top here. Assume, that was the only time we used that word. Assume f has more than one root. So therefore, f cannot have more than one root. It either has no roots or 1. But we've already shown that f does have one root by the intermediate value theorem. Therefore, f only has one root. So this implies, oops, I'll use a different color there. F has only one root. Okay, so that's just a review of a problem we did a long time ago. But now we're going to approximate this root using Newton's method. Perfect. Well, we know our derivative. It's, where is it? It's this piece right here. That's our derivative. So what I'm going to do is I'm going to write down the tools I need to use Newton's method to approximate the root. Remember, the root is somewhere on the interval from -1 to 0. We know it's not at -1 because, well, we know the value at -1, and we know it's not at 0. Okay. We also know that f prime of x, third time I'm writing it down, but here it is. It's 7x to the 6th plus 20x to the 4th plus 3. And you could take a wild guess on this interval for your first guess at the root. So your x sub 1 is just going to be your first guess. It doesn't have to be actually at the root, it just has to be near. Well, any value will do. And in fact, you could technically, even though we know that, for example, f of 0 is definitely not the root, or 0 is not the root, I could still let my initial guess be 0 because the derivative at 0 is not near to 0, it's 3. So that's going to be very useful. And then we can compute x sub 2 by taking x sub 1, subtracting f at x sub 1, dividing by the derivative at x sub 1, and we would get 0 minus, I need to also write down f so I can have it in front of me. So let me go ahead and write down f as well. F of x is equal to x to the 7th plus 4x to the 5th. What is it? Plus 3x plus 5. All right. So evaluating that function at 0, we get 5, and 3 is what the derivative is at 0. So we get -5/3. And that will be our x sub 2. So x sub 3 will be x sub 2 minus f evaluated at x sub 2 divided by f prime at x sub 2. And that would be -5/3 minus f at -5/3 divided by f prime at -5/3. And you would get some value from this. Now, let me just tell you, iterative schemes are rarely done by hand. They're usually done using a computer, or a calculator, in fact. So let me show you how to use a calculator to do this problem. I just go over to Desmos here, and I'll go up to Math Tools and just go to the Scientific Calculator. And this would work almost the same way if you didn't use Desmos. So let's say you had a regular calculator. So if you had a regular calculator, you should still do the following. You have your guess, and then you have your function evaluated at your guess. So our first guess was 0, right? And then what we're going to do, and again, this process is the same whether you're using Desmos or you have a calculator in front of you. In fact, it's a little bit faster in Desmos, but I'm doing it the way you would do it in a calculator, is you would use your answer button. So in other words, you use that last guess and you subtract off, and you start a parenthesis you start a parenthesis for the numerator, and you type in your function. Your function is your answer raised to the 7th, right? And then, what was it? Plus 4 times your answer raised to the 5th. And then plus 3 times your answer, and then plus 5. That was your function. Your derivative was 7 times your answer to the 6th, and then plus 20 times your answer to the 4th, and then plus 3. And you get this. Now remember, our initial guess was 0, and our second guess, x sub 2, was -5/3, which is a -1.6. And normally with a calculator, if you keep hitting enter, so that's what I just did, it'll repeat what you just did. So it took my last answer, -1.6667, right, and plugged it into the same formula. So that is now x sub 3 that you're looking at right here. That's the third guess. And if you hit enter again, it'll give me x sub 4, and then x sub 5, and then x sub 6, then x sub 7, and then x sub 8, right? And you can keep going. And let's say we just go to 10, x sub 9, x sub 10. Notice the difference between x sub 9, this one right here, and x sub 10, this one right here. There's no difference at all. So basically, each step of the way, we're getting closer to the root, taking our previous guess and plugging it back into this formula, taking that guess and plugging it back into the formula, and so on and so forth. And we start locking in digits. 8 gets locked in. And then 8 and 7 get locked in. And then 8, 7, 1, and 0, and 8 get locked in. Actually, yeah. And then 8, 1, 8, 7, 1, 0, 8, all of the digits that you see get locked in. So they get locked in pretty quickly. 10 iterations, basically 10 button presses. And that's how you would do it in a calculator. If you were using Desmos, let me clear all this and we'll start over again. You could do it this way. F of x is equal to x to the 7th, let's see, plus 4x to the 5th. So you basically start with your function. You just type in your function here, plus 5. And then now that that's done, you could do your initial guess, 0. And then you could type in ANS for answer, minus f at ANS, divided by f prime at ANS, and then start hitting enter. That, remember, our first guess was 0. So this is our second guess right here. Now we'll hit enter. Third guess, 4th, 5th, 6th, 7th, 8th, 9th, and 10th. There you go. So we now know that the approximate root to this equation is going to be that value right there. And I filled it in here. And this is really cool. The uses of Newton's method are really broad. We could do a lot of stuff with this. So again, this is a good example because it pulls together everything you're learning in calculus to prove that there is, using the intermediate value theorem to prove there's a root, and then using Rolle's theorem to prove there's only one root, and then using Newton's method to actually find that root. That's really very, very cool. And if you are going through a calculus class in the order that my videos are presented, that means that you've gone through graphing. And when you do graphing, you often get these roots or x-intercepts that are terrible to approximate because they're like, 5 over root 3 or something like that. You could actually use Newton's method to approximate those values. So this pulls together everything. Again, I want to reiterate before we begin this example that you do not want your derivative for your guess to be near to 0. But there are other things you have to watch out for, and this is a good example to showcase that. I've actually adjusted the interval for this example so that it can showcase that a little bit better. So here we are, use Newton's method to approximate the solution to this equation correct to 6 decimal places. Well, when you're using Newton's method to approximate a solution to an equation, it's actually nice to shove everything to one side. The left-hand side or right-hand side, it actually does not matter. I'll move everything over to the left-hand side. And what we're going to do is once we get everything onto the left-hand side here, you notice that we have an equation equaling 0. The solution to the first equation is the same as the solution to the second equation. But what we're going to do is let f of x equal that left-hand side. And it becomes the same question we were dealing with in the last example. When is this function going to hit the x-axis? Well, the very first thing you need to do if you're going to use Newton's method is make sure that this function is continuous, which it's exponential, polynomial, and trigonometric functions, none of which have domain issues, so it's definitely continuous, and it's differentiable. So f is continuous, and then if you take its derivative, f prime of x, which is not a pretty derivative, negative 18 x e to the negative x squared sine of x. I'm using the product rule here. Plus 9e to the negative x squared cosine of x. And then we'll take the derivative of these polynomial terms. plus 1. So notice that this derivative is still a polynomial mixed with some exponentials and some sines and cosines, all of which are continuous everywhere. So this function is not only are they continuous, but we know they're differentiable everywhere. So f prime is differentiable everywhere. So f prime exists, let's say, for all real numbers. Right? That's just kind of critical because you can't use Newton's method on a function that's not continuous or not differentiable. So a function that has kinks, cusps, or corners, that is going to be impossible to use Newton's method on. And then functions that have jump discontinuities, same thing. All right, so let's go ahead and use Newton's method. Our first task is really to make a guess. Remember, the method itself is x sub n plus 1 is equal to x sub n minus f evaluated at x sub n over f prime at x sub n. And if you take a look at the interval they've given us, they tell us they're insinuating there's a solution on this interval. You want to, if you're going to grab an edge point, you'll want to check the derivative at that edge point. Because if your first guess is at a point where the derivative is near to 0, you've got problems. So probably of those 2 points, the 2 is the easier one to plug into your derivative. Although, to be honest with you, sine of 2 is not something that I'm willing to take a guess as to its value. However, another thing you can do is start running Newton's method. And if things go wacky, you know that you've started with a bad value. And that's generally how it works, is that within the first 2 or 3 iterations, if the numbers are varying wildly, then you know your initial guess was terrible, right? We're told there's a solution on this interval. So if our first guess leads us outside of that interval and things start going wacky, then we know we need to restart with a different guess. Our first guess, I think, should be 1/2, and that's only because I want to showcase something. So if our initial guess, x sub 1 is 1/2, now we're going to go ahead and go to a calculator and plug that guess in. So I'm in Desmos right now, and I'm just going to plug in my first guess, which is 1/2. I'll just do that right there. And then I'm going to just type in the function f of x is equal to, and I'll pause the video for this. And something critical I need you to understand immediately is that calculus does not work well with degree mode. You need to be in radian mode for this problem. I was just about to start, and then I realized, ooh, this calculator's in degree mode, and calculus breaks under degree mode. So you want to be in radian mode for this. Pretty much for any type of problem which involves trig functions in calculus, you want to be in radian mode. All right. So we're going to take our guess, and we're going to, oops, I should have typed my guess first. So my guess right now. So there's my guess. Now I'm going to take that guess, and I'm going to subtract off f evaluated at that guess, and then I'm going to divide by f prime, again, evaluated at that guess. And you see that our next guess is outside of that interval. That has me somewhat concerned. Remember, our interval went from 1/2 to 2, and it's telling me my next guess is outside of that interval. And that's a problem. If I hit enter again, oh, I'm back into the interval. No, I'm not, because it starts at 1/2. So I'm not even near to the interval again. Now I'm negative. Notice this is not getting anywhere near my interval. I wonder why. Well, the reason why is because the first guess is bad. Here's the graph of our function. And if you zoom in between 0 and 2, there are actually 2 roots. And by taking a guess at x equals 0.5, our tangent line shot us back over to this x value right here. And it created a tangent line that shot to here, and then it started kind of targeting this wrong root. So there is a good example of starting and getting a bad guess. You know you have a bad guess if you iterate and your iterations just start bouncing all over the place, let's say they go to 300 and then negative 5,000 and whatever, then you know your initial guess was bad. So you need to start over. Starting over, I'll go ahead and let's start with a guess of 1. Again, just assuming that we have not seen the graph. We'll take the answer, subtract off f evaluated at the answer, and divide by f prime evaluated at the answer. And now I'll just hit enter a few times and you'll see we have zoomed into the 0 very quickly. How quickly? Well, let's see. Our initial guess, x sub 1, was 1. Here's x sub 2. Here's x sub 3. X sub 4. And then at x sub 5, we have a lot of accuracy. We only wanted 6 digits. And notice we locked in 6 digits actually at x sub 4. Is that what this was? 1, 2, 3, 4. Yeah, x sub 4. The 4th iteration. And actually, technically, x sub 4 is the 3rd iteration. So after 3 iterations, we got 6 digits worth of accuracy. That's pretty good. So the answer to this would be 1.33981. Technically rounded to the 6th decimal place would be 5 there. All right. So that's Newton's method in action. So in this problem, we're asked to use a linear approximation to estimate the value of this radical. And then we're going to use Newton's method. I like this problem because it's a good review problem of linear approximations. So as I've taught my students, if you're going to do a linear approximation to approximate the value of something like this, you'll look at the base function. The base function here is the 6th root of x. So we're going to let g of x, I'm going to call it g because I'm using f for something else. We're going to let g of x equal the 6th root of x. Okay. And we want to approximate g of 58. So approximate, whoops. Approx. And so to do that, we're going to find the tangent line to g at an easier value. An easier value to take the 6th root of would be 64. The 6th root of 64 is 2. 2 raised to the 6th is 64. So building a tangent line at x equals 64. To build a line, you need 2 things, a point and a slope. Well, 64 comma g of 64 would be the point, and that is 64 comma 2. Okay, so that's the point. And now we need the slope. Well, that'd be g prime at 64, but let's find out what g prime of x is first. That'd be 1/6 x to the negative 5 over 6 power. Now we'll go ahead and say, therefore, g prime at what are we doing this at 64? So the slope of the tangent line at x equals 64 is 1/6 times 64 raised to the negative 5 over 6 power. And you say, I can't calculate that by hand. And I say, yes, you can actually. That's 1/6 times the 6th root of 64, and that is raised to the 5th. Well, the 6th root of 64 is 2. 2 to the 5th is 32. So that's 1/6 times 32. That's, what is it, 192. 1/192. Let me just double check that. Yep, that's right. Checking everything else. 232. Yep. So there we go. So we have a slope and a point. So our line, our tangent line equation is y minus the y value is equal to the slope times x minus the x value. And now we're going to go ahead and solve this for y. That's 2 plus 1/192 times x minus 64. And this tangent line is very, very much close to the function when x is near to 64. Well, 58 is near to 64, so g of 58 is approximately this linear function at 58. So g at 58 is approximately L at 58. And L at 58 is 2 plus 192 times 58 minus 64. Well, 58 minus 64, is that a negative 6, I think? Yeah, negative 6. And now I'll start reducing. Let's see. Oh, that is completely divisible by 6, actually. That's going to be 2 minus 1 over 32. Or in other words, 1, 32, 64, 63 30-seconds. Okay. So we get that value for the, the 6th root of 58. That's the 6th root of 58, the approximate value for it. 6th root of 58 is 63 over 32, roughly. And if I were to grab a calculator, which kind of defeats the purpose of using this linearization method, but if I were to get a calculator and see how good this approximation is, we get this fraction to be 1.96875. Now we're going to switch gears. So that's using an old method. Now we're going to switch gears and use Newton's method. Now, how the heck would you use Newton's method to approximate that value? I'll use blue for Newton's method here, or maybe green. Green is good, right? So for Newton's method, we'll let x equal the 6th root of 58. We don't know what that is, so I'm just going to say let x equal that. But once you let x equal that, that implies x to the 6th power is actually 58, which implies x to the 6th minus 58 is equal to 0. And if you let f of x equal x to the 6th minus 58, you're just asking, when does that cross the x-axis? So I know that's a continuous function. It's also differentiable. So let me just take its derivative. There we go. And I'll take a wild guess as to what the root is. We kind of already know it's roughly near 2. So let's go ahead and guess 2. Our initial guess will be 2. Why not, right? Because if somebody just walked in the room and said, I need the 6th root of 58, I'd probably say it's somewhere less than 2, but around 2. So let's go ahead and do this. If our first guess is 2, remember, our next guess in line will take that previous guess and subtract off f at that previous guess divided by the derivative of f at that previous guess. Going to a calculator and remembering that our function is x to the 6th minus 58 and our derivative, well, is 6x to the 5th. So I've typed in the function here. I'm going to type in my guess, which is 2. And then I'm going to take that answer, subtract off f evaluated at that answer, divide by f prime evaluated at that answer, and start hitting enter. So this is the second. And by the way, I think we wanted 8 decimal digits of accuracy. So let's see. Sorry, I'm trying to get my cursor over there. That's the first. That's technically our first guess. Second, third, fourth. Let's go ahead and hit enter for the fifth. Oh, fourth, locked it in, right? Fourth, x sub 4 is going to give us that value. A couple things I want to mention here. One, actually a few things I want to mention here. When they say they want 8 digits of accuracy, I'm really looking, I hit enter enough times until I see 2 answers or 2 iterations in a row where they're identical out to 8 digits, right? So 1, 2, 3, 4, 5, 6, 7, 8, right to there. So I want my 2 answers in a row to be locked in at those 8 digits. Once I get that lock in, that lock happened one step previous. And that's why I said it happened at x sub 4, because this is x1, this is x2, this is x3, and there is x4. Also, I said in the previous problem, this is the 3rd iteration. Even though it's x sub 4, it's technically the 3rd iteration, and that's true. This, too, is your guess. This is your first iteration, second iteration, and the 3rd iteration, which sucks with the book that I use, because the book that I use, they call this x sub 4, but most of us would call that x sub 3, and we'd call our initial guess x sub 0. So that's just a little heads up, but if you're working out of the Stewart calculus book, it's going to always start with x sub 1, not x sub 0, which is opposite of what, or different than what real applied mathematics follows. The next thing I want to mention here is that we might as well go ahead while we're at the calculator screen and see what what Desmos says is the 6th root of 58. So 58 raised to the 1/6 power, which is the 6th root, is, look at that. We have all their possible represented digits there. I wonder if you can, nope, I was seeing if you can increase the number of digits here, but you can't. But in any case, there we go. We have that great approximation. And it is much better and actually much faster than using linearization. And that's why I like to teach this topic. It's such an easy topic to teach, a really fun topic for students, very easy and very applicable. The final example we're going to do here is really bringing back in the optimization style problems. So when you did optimization with calculus, we had to grab calculators all the time because our answers were always really messy. Turns out you don't really need to, well, I guess you're still grabbing a calculator, right? You're using Newton's method. You're just approximating those values using a different method rather than just typing in numbers. So let's see how that works here. Use Newton's method to find the coordinates correct to 6 decimal places of the point on the parabola that is closest to the origin. This is an optimization problem because what you want to do is minimize this red distance here. I'm going to call that distance a capital D. But that distance you want to minimize. You want to find out what's the shortest distance between a point that's on the parabola, x minus 9 quantity squared, which is that black parabola right there, and the origin. What's the closest distance to the origin? So in this point, we'll call x comma y because we just don't know what it is. But you can use the distance formula here. And so this is a very much a problem that we did in the optimization section. It's just we get to use Newton's method for it. So the formula for the distance using Pythagorean theorem is just that d squared is equal to the difference between the x values squared plus the difference between the y values squared. And we can go ahead and take the derivative of both sides. Let me actually just write this as d squared is equal to x squared plus y squared so that we have this. But the problem is that for this to be an optimization problem, you do not want this many variables in here. So I'd like to relate out one of the variables. We only want 2 variables in an equation, not 3. Luckily, we're given that where this point exists, the y value is the function value at that point. That is, the y value is the quantity x minus 9 and quantity squared. So I could replace y with x minus 9 squared. That's what I'm going to do here. I'm sorry that I'm using the red ink. That's usually not what I want to do, but so it's going to be x minus 9 squared squared, which is x minus 9 to the 4th. And now you can go ahead and take the derivative of both sides. I'm doing this implicitly. You technically do not have to do this implicitly, but I'm just doing this implicitly because I want to. It also affords me the opportunity to talk about something that I forgot to talk about in my videos on optimization. And that is, when you're doing optimization, you're really looking for critical numbers of your function d in this case. And those critical numbers occur where your derivative, d prime, is 0 or where the derivative does not exist. Well, since d is a distance, d will always be positive. Mainly because if you take a look at our graph, you can easily guarantee d will always be greater than 0. So since d is not going to have, we're not going to have domain issues for d, I don't have to worry about dividing both sides by that statement right there. Well, I could divide everything by 2 at least, so let me at least do that. But I don't have to worry about the other part, which is when does this derivative not exist? It always exists because again, this d, if you were to bring it over and divide both sides by it, it would never become 0. You would not have a 0 denominator, which means that we're just going to let d prime be 0. And when you do that, this whole left-hand side disappears and you're just solving 0 is equal to x plus 2 times the quantity x minus 9 and quantity cubed. So we want to know what is the solution to this following equation. 2x cubed, let's see, minus 9 times 2 minus 18x squared, plus 81 times 2, 162x, which I have to add to this x as well, so I'll call it 163x. And then minus 9 to the third times 2. Whatever 9 to the third is. I have to grab a calculator for that. It's 1458. So there we go. All right, so we want to solve this equation. Well, I'm going to go ahead and call this right-hand side f of x, and I'm going to take a guess as to what the solution is. Well, now I really need to know, because I need to take a good educated guess. I'm going to say that x equaling 8 will be my initial guess. Remember what x stands for. It's the x value of the coordinate that is closest to the origin. So I'm just going to guess that 8 is the solution, just because it seems like it should be. And then I will work from there. So let's go ahead and do this. So my x sub 1 is 8. And we're just going to, again, use Newton's method. The next guess in line will be that 8 minus f evaluated at that 8 over f prime evaluated at that 8. Let's go ahead and do this. So I have this set up. Now I'm just going to I'll type in my initial guess, which is 8. And I'll take that answer, subtract off f evaluated at that answer, and divide by f prime evaluated at that answer. And now I will hit enter a few times. Didn't actually take too long, did it? Let's count up what x sub we're at. So this is x sub 1, 2, 3, 4, 5. At x sub 5, we get it locked in. So that's pretty good. Now remember, that is the function value where, that's the x value of the point where that function is closest to the origin. And they want the actual xy coordinate, so I'm going to find the y coordinate just by taking that answer and plugging it into f. That's all. And that y coordinate is very small, nearly to 0. So I'm going to go ahead and write that in. Actually, there's really no reason for me to write that in because we have all the information we need. So the answer is the point is 8.972222355, and the y value is 2.27 times 10 to the negative 13th. That is not 0, actually. It's close, though. But yeah, that's the answer to that question. Very, very fun question. All right, that does it for this video, and that does it for Newton's method.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.